Hi, so before we move on to something that's called Le Chatelier's principle, sort of the final piece of equilibrium that actually doesn't have any math associated with it. This is a sample FRQ from a long time ago, but it's got a little bit of everything in it. So I'm hoping we can use this as like a progress check, sort of halfway through this chapter to see how we're doing. So if you want to, take 10, 15 minutes or so, try this question all the way through. There's tons of parts to it. And then you can come back to this tape if you want to just like fast forward to the end and see all the answers. You can do that, or then just watch it, and see how you did. So the question is talking about a 1 mole sample of hydrogen iodide gas placed into a evacuated container. There's the balanced chemical equation, and we have a graph of the concentration of HI versus time. So the first thing that it asks is for the Kc. So one thing I want to make sure is that these are gases, but since it says Kc, that's telling me that the question should be in terms of concentration. And products are going to be H2 and I2 over the reactant, which is HI, and the coefficient is 2, so that's going to be squared. Then the question says, what is the HI at equilibrium? So on yours, you can see that there's a graph. This is really just testing, do you realize that once the concentration stops changing, that's when equilibrium has happened. So that's going to be 0.80, and that's and so with the, it's just 0.80 molarity. Make sure you have the unit there. Determine the equilibrium concentrations of H2 and I2. So that is going to be an ice chart, basically. So we write the balanced chemical equation. And remember, ice is initial change equilibrium. Initially, the question tells me that we start out with 1.00 molarity. And we know that the final equilibrium value of the HI is 0.800 molarity. So I can assume this goes down by 0.2. Let me erase that. By 0.200, and that means that these guys must go up, because the opposite side, if one side goes down, the other side goes up. Because their concentration is half of H2, these guys go up by 0.100 for an equilibrium concentration of 0.100 for both of them. D says on the graph, show the concentration of H2 over time. So what we're looking for here would be showing that it starts at 0, and at about the same time as the HI reaches equilibrium, we want the H2 to reach equilibrium, and it should reach it at a concentration of 0.10. So it should look something along those lines. And then calculate the value of Kc. So the value of Kc will be, all we need to do is plug in the values that we had previously done. So 0.100 times 0.100 over 0.800 squared, and that comes out to be 0.0156. Part F. At 1,000 Kelvin, the value of Kc is 2.6 times 10 to the negative 2. So remember, Kelvin, or the temperature, is what can change the equilibrium constant. So this is like a whole different scenario here. We're taking 0.75 moles, 0.1 mole of H2, 0.5 moles of I2. We're placing it in a container, allowing it to reach equilibrium. And now we have to determine which way the equilibrium will shift in order to reach equilibrium. So determine whether the equilibrium constant of HI is greater than or less than. So that's how the question is asking us that. So this is a scenario where we're given concentrations that are not at equilibrium. So we're going to find Q, and then can compare Q versus KSP. So that would be, it's the same thing as the equilibrium constant, just the numbers are not at equilibrium. So I plug in 0.10 times 0.50 over 0.75 squared, and I get 0.088. And I actually changed that to 8.8 times 10 to the negative 2, just to make it easier to compare with the equilibrium constant that's given to us. And I can see that it is, in fact, bigger than the equilibrium constant. So in order for Q to become K, it's going to have to decrease. And since it's basically it's products over reactants, that means the amount of product is going to have to come down. The amount of reactant is going to go up. So the equilibrium is going to shift to the left. Remember that the balanced chemical equation is this chemical equation. So if it shifts to the left, that means there's more HI will be produced. And that's what the question is asking us. Will the equilibrium concentration be greater to or less than the initial concentration? And it will be greater to.